Hello, Patil, Pallavi. Shall we start? Yeah, we should wait for 2 to 5 minutes. Okay, we will start. Today we are going to discuss about the shear force and bending moment for UDL load, that is uniformly distributed load. We are going to see nature of SF diagram and bending moment diagram for UDL load. The question is a simply supported beam of a span L carrying UDL W kilonewton per unit length over entire span as shown in figure. Okay, so this is simply supported beam and load on the beam is only UDL type load and intensity of load is given W kilonewton per meter. Okay, L is the length of a beam. Then first we need to draw freeboard diagram. While drawing the freeboard diagram, we need to replace hinge support. Here are the two hinge supports. While replacing the hinge support, we always take two reactions, one vertical, one horizontal, right? So here I have taken two reactions at A point and two reactions at a B point. Then to solve these unknown reactions, we need to use equilibrium condition, that is summation fx equal to 0. If summation fx equal to 0, here we can see ax minus b equal to 0 because ax acting in a rightward direction and bx acting in a leftward direction, right? So ax minus bx equal to 0. Okay, then we can say x equal to bx. Now next, uh, we can use another equilibrium condition, that is summation fy equal to 0. Summation Fy equal to 0 means the forces which are acting in a y direction, or here we can say the forces which are acting in a vertical direction. Okay. So this Ay plus By equal to minus Wl. Why this minus Wl? Because we have converted this UDL into point load. So this uniformly distributed load we converted into point load. So intensity of is W kilonewton per meter, right? Means for each meter the load is W kilonewton, but our length is a L. So due to that, here we have taken WL kilonewton. This WL means only WL kilonewton. Don't take it is as a W is kilonewton, L is a length meter. So it will be kilonewton meter. Don't think like that. Okay. Then now we'll take a moment. Moment about point A equal to 0. Okay, this is the third equilibrium condition. I will take a moment of WL force. Moment of this WL force into perpendicular distance, that is L by 2. Okay, W into L by 2. And moment of this WL force is a clockwise movement. Okay, and minus By into L. Minus By into L. This force is By and L is the perpendicular distance. And movement of this force is anti-clockwise. So By equal to WL by 2 kilonewton. Okay. Now we'll see how to calculate SF and bending moment. So in left part, I will solve for the SF calculation, right part for the bending moment calculation. So as per critical points rule, we need to do SF, we need to take SF section at all at all point load, means at a just left of point load, just right of a point load. Second rule is at the start of UDL, at the end of UDL. Third is at the start of UVL, at the end of UVL, because these are the critical points. Means critical point means at that point SF value changes drastically, right? So to know that drastic change, we should take section at all critical points, right? So here as per the critical points rule, we have taken 4 section. Here is the point load, that is, or we can say vertical reaction. So here we have taken 2, just left of vertical load, just right of vertical load. Simultaneously at that this point UDL start is also there. So always give preference for more number of sections. Okay, so here we have taken 2 sections, and at the extreme end there is also vertical load and end of UDL, right? So here for the vertical load, as per rule, we need to take 2 section, just left of vertical load, just right of vertical load. So here also we'll take 2 sections. Now SF at section 1 1. Now follow the sign convention rule. Sign convention, if we take a section, if we consider left part of the section, then treat upward forces positive, downward forces negative. Okay. Now SF calculation, SF at a section 1 1, or we can say SF just left of A, means at this section, section 1 1. Now beams goes in the right part, in the left part no beam region, right? So we can say SF at section 1 1 equal to 0. If we do the calculation for the right part, then also we'll get the same answer, that is 0. Now we'll take section 2 2. Consider section 2 2. Now forget about this section 1 1. This section 2 2, divide the beam into 2 parts, left part and a right part. Okay. So in the left part, how many forces? There is only one force, that is WL by 2. Okay, this WL by 2, and according to definition of shear force, it is just algebraic sum of vertical forces of a left part or right part of the section. So according to this, here we'll get WL by 2 kilonewton shear force at section 2 2. Now consider section 3 3. This section 3 3, divide the beam into 2 parts, left part and right part. Concentrate on the left part only. Now check how many forces acting on a left part of the section 3 3. There are the 2 forces. One is W by 2 and this UDL, pole UDL, right? So here for section 3 3, SF will be WL by 2, this vertical force, and we need to convert this UDL into point load for the calculation purpose only. Okay, so UDL is a UDL load in a point load is equal to WL. So here I have taken WL minus WL because downward force is negative. Okay, so finally we'll get SF at a section 3 3 equal to minus WL by 2. Okay, and at a section 4 4, value of SF equal to 0, because if we consider right part of this section 4 4, there is no beam region, so we can say directly SF equal to SF at a section 4 4 equal to 0. Now we'll solve for the bending moment. We'll do the bending moment calculations. So as per critical point rule for the bending moment, we need to calculate bending moment at the point load, or we can say at the vertical load, at the start of UDL, at the end of UDL, at the start of UVL, at the end of UVL, and whenever concentrated movement is present on the beam, at that time we need to take section just left of concentrated movement just right of a concentrated movement. Okay. Now sign convention. If we consider left part, always treat positive movement, clockwise movement positive, anti-clockwise movement negative. Okay. And for the right part, anti-clockwise movement positive and clockwise movement negative. Generally, try to consider left part. Now, bending moment at a section 1 equal to 0. Now, bending moment at a section B is also 0. So, bending moment at section 1 equal to 0, at section 2 equal to 0. But at intermediate stage, there should be a bending moment because UDL load is acting on the beam. Now, to calculate the bending moment at intermediate stage, we need to take a section ESS, and to know the nature of bending moment also, we have taken section ESS here at a distance of x from the left hand, right? Now we'll write the bending moment equation about the section ESS. So now this section ESS divide the beam into two parts. This is left part, this is right part. Consider left part only. In a left part, how many forces acting? First, this WL by 2, and second, this partial UDL up to section SS, right? So this W, then according to definition of bending moment, we need to take algebraic sum of moment of left part section, right? So WL by 2 into this x distance, WL by 2 into x, WL by 2 into x, and moment of this partial UDL. So we know that intensity of UDL is W per meter, right? But our length is a x meter. So total load of this partial UDL is W into x, W into x, and it will act at the center of x by 2 distance, right? Wx into this distance is x by 2. This distance is x by 2. So here we can write Wx into x by 2. Moment of this partial UDL is Wx into x by 2. I have taken here minus sign because this moment is anti-clockwise, right? And it is at the left side of the section. Okay. So finally, bending moment at a section is WXL divided by 2 minus WX square by 2. So means we can vary this x from 0 to L, right? If we put x equal to 0, we'll get bending moment 0. If we put x equal to L, means at a section 2, we'll get the bending moment again 0, right? Now observe this equation, bending moment at a section ESS. You can see this bending moment between UDL span varies with respect to power of x, and this power of x is a 2. This power of x is a 2. So means it follow the second degree curve, similar to parabola. So for whenever there is a UDL load, at that time we need to draw second degree curve, and for SF diagram we need to draw inclined straight inclined line. Okay. Now to calculate the bending moment at a center, we will see here. Okay, we'll see after drawing the SF diagram. So SF diagram, just I have copied the SF calculations, then draw baseline, our critical points A and B. Now we know that SF just left of A is a WL by 2, and just left of B is WL by 2, right? Now we want to join these 2 points, but to join this point, we can see here as the length varies. If we take section here at a distance of L by 4, we'll get the different value from this WL by 2. Means if we take section here, so we'll get WL by 2 minus W into WL by 4. WL by 2 minus WL by 4. So here we'll get the value WL by 4. So this value is less than WL by 2, right? So means we need to join this WL by 2 with this minus WL by 2, right? Means I want to say whenever there is a UDL span in between vertical loads or on the beam, at that time SF diagram should be inclined line because it follows the straight line equation, right? So if we plot at a number of points, you can see that follows the straight line equation. So for that purpose here, we need to join WL by 2 positive to do minus WL by 2. So to check the nature, we have taken section ESS at a distance x. So here you can see at a section ESS, SF equation will be WL by 2, this WL by 2, and this partial UDL W into X, the minus W into X. So this, you can see this WL by 2 is a constant, and because this X is varies from 0 to L, so this is variable. So we can see it follows the straight line equation. This is the straight line equation similar to y equal to mx plus c, right? So c is a constant and x is a variable. So it follows the equation of a straight line. So whenever there is a UDL span, we need to draw inclined line. So here I join the 2 points with the inclined line. Now we'll see bending moment diagram. Just I have copied the bending moment calculation. Now bending, to draw the bending moment diagram, baseline is equal to the load diagram. Then we know that bending moment at point A equal to 0, bending moment at a point B equal to 0. So it is impossible to draw the bending moment with this A point and B point. But there is another critical point that whenever SF changes its sign from positive to negative, then also we need to calculate bending moment because there is a drastic change at that point. So here this SF diagram changes its sign from positive to negative, and in this point we'll get a maximum bending moment. Okay, because here shear force effect is a 0. So at this point means we can see this is WL by 2 distance, this is WL by 2 distance, and these two triangles are a similar triangle. So we can say this distance is a half distance of a total length. So this distance will be L by 2. So we need to calculate bending moment at a distance of L by 2, means at a center of a beam length. So put x equal to L in this bending moment equation. So if we put the x equal to L by 2, we'll get the positive value, that is WL square by 8. Now plot the value WL square by 8. And the nature of bending moment diagram is second degree curve. Why second degree curve? Because if we have taken section in between UDL span and we observe this equation, that equation shows that bending moment varies with respect to power of 2. So due to that, here we need to draw second degree curve. So this is related to the bending moment. Okay. Do you understood this concept of shear force and bending moment between UDL whenever load is UDL? Do you understood? Please give your reply. Then we will move for next problem. Yes, okay. Now we'll solve one problem. So I've taken problem from the solid mechanics. So this will clear about how to draw the SF and bending moment diagram whenever UDL load is given. Okay. Now in this problem, there is a one UDL load and one point load. This is again simply supported beam. At A point there is hinge support, and at the D point there is a roller support. First step, we need to draw the free body diagram. And while doing the calculation of a reaction, we need to convert this UDL into point load. So intensity of UDL is at 2 kilonewton per meter. Once again, I will repeat, 2 kilonewton per meter means for every meter load is at 2 kilonewton, and that UDL span is a 4 meter, means total load equal to 2 into 4, that is 8 kilonewton. Due to that, here I have taken 8 kilonewton. I have replaced this UDL by the point load, but don't consider this is a point load while doing calculation of a SF and bending moment. Also drawing the SF and bending moment diagram. Then use equilibrium condition to find out the reactions. Summation Fx equal to 0, Ax equal to 0. Then use second equilibrium condition, summation Fy equal to 0. Ay plus dy equal to minus 5 minus 8 kilonewton. So in this way we will get to equation number second, that is Ay plus dy equal to 13 kilonewton. Okay. And third equilibrium condition, that is summation of moment about point A equal to 0. So moment of this 8 kilonewton force, 8 into 2 meter, 8 into 2 meter, and this moment is a clockwise. Okay. Then moment of 5 kilonewton force, 5 kilonewton into 5 meter distance. Okay. And moment of dy force, dy into this total distance, 4 plus 1 plus 4 plus 1 5 plus 2 7, dy into 7, and this moment of dy is negative because it is anti-clockwise. It is in an anti-clockwise direction, right? So if we solve this equation, we'll get dy equal to 5.86, and if we put the value of this dy in an equation, second equation, then we'll get the value of Ay equal to 7.14 kilonewton. Okay. Now we'll do calculation for the SF and a bending moment. Now here you can see, or please keep in mind, always take a section on a load diagram only. Don't take a section on a free body diagram. You can see here, if we take a section on a free body diagram, here we have converted UDL into point load. Its meaning is changing here. Actually, we have taken for the calculation purpose. This doesn't mean that this is the point load. So due to that, always take section on a load diagram. So here you can see how many sections I have taken: 1, 2, 3, 4, 5, 6, and 7. You can see again, by the critical points rule, we need to take a section just left and right of a point load, any point load or any reactions. So here is one reaction, another reaction is at the end point, 5 kilonewton is a vertical load, right? And second rule is at the start of UDL, at the end of UDL. So here I have taken two reactions, two sections, because for the vertical load we need to take just left and right, but for the UDL we need to take on just start of the UDL, but always give preference for the more sections. So here I have taken two sections, then at the end of UDL another section, right? So in this way I have taken seven sections. Now SF at section 1 1. If we take this section, if we consider this section, beam goes in a right side. So in the left part there is a no beam portion. So we can say SF at 1 1 equal to 0. If we solve for the right part, again we will get same answer 0. Now SF at a section 2 means just write off this A point. Just write off this A point. So if we take here section, it divide the beam into two parts. This is left part. This is right part. Okay. So in left part there is only one force, that is 7.14 kilonewton, and it is acting in a upward direction. Okay. So 7.14 kilonewton in upward direction, and take upward forces positive. Sign convention, you can see, if we consider left part, treat upward forces positive, downward negative. So due to that I have taken here positive. Then go for the section 3.3. Now again this section divide the beam into two parts. Now forget about the other section, just concentrate on the section 3.3 and consider the left part of the beam. Now there are the two forces. One is 7.14, which is acting in upward direction. Another is a whole UDL acting in a downward direction. Right. So SF at a section 3.3 will be 7.14 minus 8 kilonewton. I have taken here minus 8 kilonewton because for the calculation purpose we need to convert this UDL into point load. Okay. So here minus 8 kilonewton. In this way we'll get the answer minus 0.86 kilonewton at point B. Okay. Now section SF at a 4.4 section. This is our 4.4 section, just left of C. Now again there are the two forces at the left side of the section 4.4. So we'll get the same answer, section 4.4. Now section 5.5. Now if we consider section 5.5 and if we consider left part, there are the three forces. 7.14 kilonewton, which is acting in upward direction, 2 kilonewton per acting in a downward direction, 5 kilonewton acting in a downward direction. So according to sign convention rule, again I have written here 7.14 positive, minus 8, minus 5. So I will get answer here minus 5.86. Okay. Then section 6.6, which is just left of D. Right. So in this case we can solve for the right part, because in right part only one force, that is 5.86. But for the right part, sign convention is treat downward positive and treat upward forces negative. So if we consider section 6.6 and if we consider right part, then this 5.86 acting in a upward direction, but as per sign convention upward force is negative. So due to that, here I have written minus 5.86. Actually I solved for the left part, but here you can solve by considering right part. Okay. Now say SF at a section 7.7. SF at a section 7.7 equal to 0, because beam goes in a left side, in a right side there is no beam region. So we can say directly SF equal to 0. Now bending moment calculation. For the bending moment calculation, again we can see here I have taken 4 section only: at point load, at UDL end, at point load, at a point load, as per the critical rule, critical point rule. Now bending moment calculation at a section 1 means we can write directly bending moment at A point. So bending moment at A point equal to 0. If we divide the section divide the beam into at this section, beam goes in the right part, and if we consider left part, there is no beam region. So directly we can say bending moment at A equal to 0. Bending moment at B equal to now there are the two forces at the left side of this section 2, or we can say at this section, this upward force 7.14 and another is whole UDL, right? So we need to take bending moment of this upward force and UDL. So moment of upward force is 7.14 into 4-meter distance, right? And second, to do the calculation of bending moment, we need to convert this UDL into point load. So I have shown here this point load, and intensity of point load is 8 kilonewton, right? If intensity of point load is 8 kilonewton, then movement is 8 kilonewton into 2 meter distance. So 8 into 2, and I have taken here negative sign because movement of this 8 kilonewton is anti-clockwise, and as per sign rule, sign convention, we need to take anti-clockwise movement negative, right? So hence here we'll get the answer 12.56 kilonewton meter. Okay. Now next section at a point C. Again, check left side of the section. There are the again two forces, but to calculate the moment distances varies with respect to previous section. Now take moment of a 7.14 force. Now check distance. Distance is 4 plus 1, 5 meter. 5 meter distance is about section at a C. So 7.14 into 5. This is the moment of this upward force. And then moment of this UDL. Now this we converted this UDL into point load, and that point load force is a 8 kilonewton, and distance perpendicular distance is this 2 meter plus 1 meter, means total 3 meters. So due to that I have written here 3, 8 into 3, and this moment of this 8 kilonewton, moment of this UDL is a anti-clockwise, so I have taken here negative. So finally we get the answer 11.72 kilonewton meter. Now bending moment at D, means at the roller support. Here bending moment equal to 0. Why bending moment equal to 0? Simply beam goes in a left part, in a right part there is no beam region. So directly we can say bending moment equal to 0. If we solve for the left part, we'll get the same answer, that is 0. Okay. Now we'll draw SF diagram and bending moment diagram. So once again I have drawn here load diagram. I have just copied the SF calculation, bending moment calculation. Now we'll see how to draw the SF diagram. You can see here SF just left of A is 0, just left right of A is 7.14 kilonewton. So I have taken here 7.14 kilonewton. Just I have plot here 7.14 point. Okay. Then at a B point, means at a SF at a 3 section is minus 0.86. So I have plot the point minus 0.86 here, just below the B. Then section 4 means at a C. At C value is again minus 0.86. So I have plot here minus 0.86 point. Okay. Then SF at a section 5 means just left of D. Just left of D means at D. So just left of D, I have taken here 5.86 minus 5.86, and SF at a section 5 is here, just right of C. Just right of C, I got the value minus 5.86. Just left of D, also I got same value minus 5.86, and at just right of D equal to 0. So in this way, first we need to plot the points with SF values. Okay. Then for joining this from A to B section, means between UDL points, we need to draw the straight line. Okay. Then from B to C, it will show the horizontal line. Automatically we'll get the horizontal line because just right of B, at point B we got the value 0.86, and just left of B also we got the value 0.86. So here we have drawn horizontal line, but just right of C we got the value minus 5.86. So I have drawn here vertical line, and just left of D again I got the value minus 5.86. So I have drawn here horizontal line, and finally 0. So I have connected this minus 5.86 to the 0. Okay. Now we'll go for the bending moment diagram. Now bending moment diagram, again base length is equal to load diagram length or SF length. Okay. Now again consider all critical points A, B, C, D. At A point, value is 0. Okay, so I'll put here point 0. At B point, value is 12.56. 12.56. At a B is 12.56. So just I plot here positive value 12.56. At C point 11.72. So above this C point, I have plotted the 11.72, and at the D 0, right? But another critical point is the remaining, that here SF changes the sign. Whenever SF changes the sign, we need to do BM calculation. So here bending moment, SF diagram changes the sign, but we don't know what distance this SF changes the sign. Okay. Now we know that this distance is a 4 meter. This total distance is a 4 meter. Let this distance is a x, then this distance will be 4 minus x. Now consider these two triangles. This is first triangle and this is second triangle. Both triangle are a similar triangle. If we solve by the similar triangular property, height by base, 7.14 is the height of a triangle, first triangle, and base is x, 7.14 by x, equal to height of this triangle is 0.86 and base is a 4 minus x, 0.86 divided by 4 minus x. So we'll get x equal to 3.57 meter. Here don't consider minus 0.86 because we are solving the two similar triangles. So don't take it minus 0.86. This minus 0.86 is the SF value. Okay. Then if we solve this similar triangle, we'll get x value is 3.57 meter. Meaning of this x equal to 3.57 meter is that SF is changing sign, or a value of SF is 0 at a distance of 3.57 meter. So we need to take bending moment at this section. So calculate the bending. Let this point is a E point. Calculate bending moment at E point. So we can write down we can take a section here at a 3.57 meter distance. Okay, now if we take a section here, consider left part only. Okay, and check how many forces at the left part. Here is the upward force, that is 7.14 kilonewton, and this much partial UDL, means up to this 3.57 meter UDL we need to consider. Don't consider whole UDL, right? Now you can check intensity of UDL is 2 kilonewton per meter, and for the calculation purpose we need to convert this UDL into point load. So 2 kilonewton into 3.57 meter distance. Because this UDL, we need to consider UDL up to section line only. So for that purpose, 2 into 3.57 meter. That will be the total load, and that total load will act at the half distance of partial UDL. Means it will act at this distance. Means at a distance of 3.57 by 2. Okay. So bending moment equal to bending moment of this vertical force 7.14 into 3.57 distance, and bending moment of this UDL 2 into 3.57, 2 into 3.57 for to convert UDL into point load, that is 2 kilonewton, and it is acting on a 3.57 meter. So 2 into 3.57 meter. Okay, and for the moment we need to take this distance, perpendicular distance, and that distance is 3.57 by 2, right? So in this way we will get the value 12.75 kilonewton meter. Okay, now this value is at E point, so just plot the point of value 12.75, right? Now check, this will be the maximum bending moment. Now we know that for bending moment nature for the UDL span is a second degree curve. So we need to join this A point, this E point, and B point by second degree curve, right? By the second degree curve. Then from 12.56, or we can say from between region B to C, again join with the straight line, and from for region C to D, again join bending moment line with a straight line. So in this way, this is the bending moment diagram, and this is the shear force diagram. One another point is important, that is point of contact fracture. Point of contact fracture means whenever bending moment changes its sign, that point is called as a point of contact fracture. But now in this diagram we couldn't find a point of contact fracture because bending moment doesn't changes its sign here. It lie in a only positive section only. Okay, so how to calculate the point of contact fracture? So to calculate the point of fracture, we need to take a section. We need to take a section anywhere. We need to take a section. Generally, take a section by guessing that where we'll get the sorry. Generally, take section in a UDL span. Okay, because in UDL span we'll get the or instead of that I will say take a section anywhere at a distance x, write the equation about the section in terms of a x, and then equate that equation equal to 0. So means we can say bending moment equation equal to 0. That meaning of that is that we are finding x value in a such a way that bending moment value is equal to 0. So we'll get the value of x, and at that this x value means our point of contact fracture. If bending moment change its sign from positive to negative or negative to positive, we need to calculate point of contact fracture. Okay, so this is related to about SFD and BMD whenever UDL load is given. Okay, do you understood? If anybody having doubt, please ask. Or you can put your doubt in a chat box. If you have any doubt, please put a message in the chat box. And please fill up this feedback form. If anybody having any doubt, you can ask. Okay, point of contact picture. Yes, I will take. So I will draw. But it will take too much time. Okay. So here movement is anti-clockwise, and this is the UDL load. Okay, intensity of UDL is a 2 kilonewton meter. And concentrated moment is 2 kilonewton per meter. At the left side, there is a hinge support. And at the right end, there is a roller support. Okay, this is the roller support. Now, if we solve the equation, just I will draw the directly SF diagram. Okay, so here I got the value 0.8, then minus 1.2. So here is the value is 0.8. Here minus 1.2. Okay, then bending moment diagram. I will show how to calculate the point of counterfactual. For that purpose only, I am copying this SF diagram, bending moment diagram. So here 0.2, value is 0.2, 0.16. Okay, here is the value 0.16. Okay, now here 0.16. Okay, I will draw at PPT, it will be better. Just keep patience. I will write the values. .16 positive here, that is maximum bending moment, minus 0.2, then minus 0.8, 0.8, okay, and then next value is 1.2, and distance is given. This UDL span is 1 meter, sorry, 1 meter. Then distance between UDL point to concentrated movement is 0.5 meter. And next, between concentrated movement to end point is 1 meter distance. Okay. Okay. Now we got the SF value 0.8 at the left of this A point. At the UDL end, we got the value minus 1.2. Okay. So and here also at the left point minus 1.2. So in this way we drawn the SF diagram. You will get all the values. Okay. But now you can see this SF changes its sign in between this UDL span. So we need to calculate this X value. So as per my calculation, this X value is 0.4. Value of X is a 0.4. Okay. And at this X equal to 0.4, we get the value of maximum bending moment, that is 0.16. Okay. And at the UDL end, we got the bending moment minus 0.2 kilonewton per meter. And at the left of concentrated moment, we got the value 0.8 kilonewton meter. And at the right, we got the value 1.2 kilonewton meter. Okay. Right. Now, this point is a point of counterfacture where bending moment changes sign. So here bending moment changes sign from positive to negative, right? And here also from negative to positive. But this distance we can easily calculate because this distance is from the left hand side, this distance is a 1 meter, or we can say from the right side 1.5 meter. So this distance easily we get, right? But here we need to take an equation, and this point lies in a UDL span. Why UDL span? Because this value 0.2 value is at the UDL end, and this 0.16 value is at a distance of 0.4. So this point lies in between 1 meter distance. So we need to take a section in between 1 meter. So I will take section here. Let this distance is X. So I will take section here. But right now I don't know the distance. Okay. So I will take a distance. I will take a distance equal to X. This section is at a distance X from the left side. From the left side. So this distance is a X. Okay. Now we need to calculate bending moment equation at this section X. So I will write here bending moment equation. BM at X distance equal to, okay. Now consider left part of the beam. So in left part of the beam, there are the two forces. One this vertical force and this UDL, partial UDL up to this, right? So point 0.8. This is the vertical load 0.8. Okay, 0.8 into distance is x. 0.8 into x. Now movement of this 0.8 above the section is clockwise. So I have taken positive. Now movement of partial UDL, that movement is anti-clockwise. Okay, so due to that I have taken here negative sign. Now movement of partial force, partial UDL. So intensity of UDL is 2 kilonewton per meter, right? But our section lies at a distance x. So distance of a UDL is a x. Span of UDL is only x. So total load equal to 2 into x. So I will write here 2 into x. Okay. Then that 2 into x only total load, and it will act at the distance x by 2 at the center of partial UDL, means at a distance of x by 2. So I will write here distance x by 2, x by 2. Okay, so in this way I will get, and we need to equate this equation equal to 0. We need to equate this equation equal to 0. Why equate to 0? Because as per definition of point of contact fracture, whenever bending moment changes its sign, so it will change sign means it need to cross the baseline, means at that point bending moment should be 0. So for that purpose we need to equate bending moment equation equal to 0. So I will write here bending moment at x equal to 0.8x minus 2x into x by 2, means we'll get here x square, sorry, equal to 0. Equal to 0. Now we can solve for this equation. 0.8x minus x square equal to 0, right? So we'll get x minus 0.8 equal to 0. Okay, so we'll get x equal to, here we'll get x, two values of x, but we know that value of x will be valid within a distance of 1 meter. That means value of x should lie between 1 meter distance only, or it should be greater than zero point 0.4 and less than 1 meter. So this value will be 0.8. We'll get, if we solve equation, we'll get the two values, but we should select only valued values, right? Valued value. Okay, so I hope you understood the concept of point of contact picture. You can solve, you can just take a okay, I will share this video. You can solve this problem. You will get SF diagram, bending moment diagram, but to find out the point of contact picture we need to take a section as per the our diagram, and then we need to calculate bending moment equation, then equate that bending moment equation equal to 0. Okay, do you understood the point of contact picture, how to calculate the, how to find out the point of contact picture? Okay, so please fill up the feedback form. After filling the feedback form you can leave the class. If you have any doubt, you can